We have been doing chapter 1B. Hold on, that's not you guys. We have been doing chapter 1B. How do you get to our calendar again? Real fast, just, I'm paranoid. You can go to my website and go find your tab, right? Or, good, or you can go to, well, RenWeb, I mean, do you guys do that for my class? I mean, I guess you could. I was thinking the classwork tab and then resources has like my YouTube channel and has, I don't know, if you're already in Google Classroom, it's pretty fast that way too. But we have a minimum day on Friday, right? Teachers have an accreditation, half-day, work-day, thingamabob that we have to get done. So school is, all right, guys. Guys, it's a little awkward. We're talking over me. We've had this conversation many times. Okay, so we have a half-day on this coming Friday. But here's the dilemma. What else do we have this coming Friday? It's the end of the first grading period, true? Now, you guys have taken your Chapter 1A quest. You've done corrections on it. My earlier TA today was writing down those updated scores. So that's going to get put into RenWeb to raise those scores a little bit. You guys also have your graphing handbook quiz that I should have gotten back, but we've been going kind of fast. And so we haven't really talked about those too much. But then we also have this Chapter 1B with only 2 sections left. So our goal today is to do Section 1.9 today, Section 1.10 tomorrow, and then we can have our test on Thursday. Now, my goal was to have it Friday, but a minimum day and a pre-cal test is an awful idea. It's just awful, 20 minutes, no, there's just not good, there's no way that's going to be productive. So we're going to do a 1-dayer on 1.9 and a 1-dayer on 1.10. Now, 1.10 is a word problem section, which can get really heavy and really bogged down, so I'm going to go ahead and split that homework like in half, just so we get the short, sweet version of it. So in some ways, it's going to kind of simplify our 1.9, 1.10. But once again, that minimum day has kind of bumped our test up 1 day. I didn't know if you guys had noticed the schedule, it had gotten bumped up. And I also wanted to let you know why we're doing like the short and sweet version of the last 2 sections. So sections 1.1 to 1.5 we're on the Chapter 1A test, and then sections 1.6 to 1.10. We split the chapter pretty much straight in half. Wow, this one is awful. Okay, let me get this back up. Just a couple of you might have still been writing notes on it, but I need to get this orientation fixed, or else it's just going to be a mess today. Okay, so 1.9. Look at the backboard. When's it due? Homework number 9? Tomorrow. So let's get as many examples done today as we can, so that hopefully tonight's homework is like, I got this. I doubt there's going to be extra time if you guys have already started. Basically, you got stuck, so I'll just try to address them in class. And if you see something up here that's like something in homework or your stuff, just be like, hold on, so you're saying, and I'll try to clarify. Okay, this little dude is not f to the -1 power, true? Instead, what is it? F inverse. The big idea that I wanted you guys to remember on Friday was, oh, I know what's wrong. Your notes didn't say it. That's what happened. So we did take notes and not have them written down. The big word that I should have... That was the big word I wanted you to remember on Friday, right? What did you guys fill in for domains and ranges? What happens with inverse functions because we switch the y's with the x's and then solve? The domain of f becomes the... Good. No, it's okay. And then the range becomes the domain of... Yeah, they wonder why. I showed them. Okay, we'll just move it up and then we'll pretend, right? That's good. But I did make you guys a quick warning note on this. Are you solving for the original y equals f of x when you switch and then solve? What should I have you write down in your notes about who this y is? Yeah, f inverse. Good. F inverse of x. When you switch that x and y. Thank you. I hear both ends. When you switch the x and y. That's the inverse that you're solving for. So we did some examples on Friday. There's one thing why it was so blank. But I think that, isn't this where we ended on the whole graphically thing? Is that right? Or we didn't even get to that page? We were here. Huh? Did we do algebraically? Okay. Yeah, I thought we had done this page before because I remember writing the word undo. I remember writing the domains and ranges switching. And that little guy was F inverse. But did we do this example yet? Okay. So here we are. New step. Example. What they're asking us to do is to find the inverse. At the end of the day, I want F inverse of X. That's the goal. Now, if you think switch X and Y, don't you kind of need a Y to begin with to switch it? So if I were you, I would rewrite this as Y equals 4X, even though that's what it means. Function notation means Y equals. So that way you can go ahead and switch the X with the Y. Solve for the Y by division, right guys? Simple one-step equation. But when you get that guy, he's not Y equals, right? Instead, he's the inverse, so that would be my inverse function of X over 4. But that's just a super basic one. They definitely get harder. Yeah. Well, oh, that was one division. Like, we shouldn't be that scared of getting that much harder. But here's the part that I need to make sure that you guys understood when you saw it in like homework directions, etc. When it says verify, because that's a weird direction. When it says verify, because that's a weird direction, right? So it will verify. I just solved for it. My math is perfect. I verified it. Check that. What they're actually trying to show you is what an inverse actually does. And that comes back to the idea of compositions of functions. It actually comes back to the idea of compositions of functions. Now, I'm going to actually peek forward really quickly because I think I have a better example with more steps. Maybe I don't. Okay, maybe I don't. We'll just do it here. When it says to verify, what we're saying to do is take f of x, and instead of plugging in, well, that's 4 times something, right? Instead of plugging in the x, you plug in the inverse, which is x over 4, right? So we're taking the inverse function, plugging it into the original. And the question is, does whatever was going on in the first function, whatever operations there were, multiplications, divisions, powers, etc., radicals, do they all cancel out and just leave x? And the answer in this one is yeah. But for an inverse, you have to be able to go both ways. Not only plugging in the inverse to the original, but also plugging in the original to the inverse. So now I'm taking my inverse function, quantity over 4, and plugging in my original function and going the other direction, just as they're asking me here, 1, 2, and here. Ooh, that skipped 2 pages instead of 1. I apologize. Once again, why are we doing this? We're doing this because to test whether or not functions, some of you didn't know what this meant, to test whether or not a function and an inverse, whether they're actually inverses of each other. Plugging in the inverse to the original should simplify everything away, and plugging in the original to the inverse should simplify everything away. Why? Because they are each other's undo if it's done correctly. So guys, does it undo this direction also? Yeah. Sorry about the orientation. I'm doing the best I can. That's algebraically though. Graphically. The identity function, y equals x, is going to be, in a sense, our line of symmetry. The identity function, y equals x, is going to be the line of symmetry. Inverse functions are reflections across the y equals x line, aka the identity line. And this one, like, they show you the picture, so it's not that big a deal. I want you guys to see a couple things, like there are corresponding points, but since it's this reflection across y equals x, it's not at the exact same x value, but its x value is the original point's y value. They correspond to each other, but since we switch x's and y's to solve for inverses, those points are all going to switch too. So they correspond, they're related, but it's going to be a little tricky in the sense of graphing. Because you guys are going to see a few things in homework where, let's see if I can make it a little bit bigger. There we go. They might give you an original function, this dude, right? And ask you to reflect it. And maybe it's not that hard for your brain to think about, but maybe it is. And if it is, here's a couple hints for you. what I would do, given some original function, trying to find his inverse function, is I would take it piece by piece. So I would draw my y equals x line. They don't always give you like a way to put it in your graphing calculator. And I would look on one side and say, hey, who's there? Well, where's my original function? There it is. And I would just copy that part. And then I would check the next one and be like, okay, now he goes on this side. Okay, then I'll go ahead and copy. Yeah, I know. You guys saw me try to do it though, right? Okay, we'll do the next part. Awkward. Turn the phone on. And then I would see it come in. I would try to copy that part. It's just not quite as easy of a reflection as just going across the y or across the x. So be aware, it can get hard, it can get tricky. But if I were you, I'd take it piece by piece. Think about it in sections, and it helps most students in the sense of the reflecting idea, especially if you have to do it just with the graph and not with the functions. But if you guys notice, what could be the parent function of this dude? Thinking back to sections 1, 6, 1, 7. Just this normal. What do they look like? So he's been shifted. I would say he's been shifted to the right and up. So what does he look like? Which parent function? Yeah, x cubed. That's what I was thinking. So then if you were to, I wonder what the inverse operation of cubing would be. Well, it'd be a little bit harder than that, though, because you would need to have a f of x minus some sort of c to shift him to the right, and then plus d to shift him up. But either way, that works. Okay, graphically, we're going to flip it, and we're going to reflect it across the y equals x line. But when we do that, something else is going to happen. Let me rearrange these notes just a little bit. Algebraically, switch x and y and solve for y. Gear cube is a little squeaky, so I've given you guys a little bit of time with it, but let's stop with the gear cube. Sorry. I don't know if anyone else was getting annoyed by the squeaks, but it's hard because you can't oil it like a Rubik's cube, so it's kind of
Yes, you.
Yeah, the gear. Well, like oil in a car lubricates and it makes it so all the parts move easily. So in a Rubik's cube. Well, yeah, I don't know what it is though. Does anybody have a Rubik's cube that moves really smoothly? Like there's competitors and they. There are ones that are made in a way that they move faster. And we also have this. This
is the one that we called at the beginning of the year.
And then they took her name off, but now she's back.
Oh wait, are you joining our class then? Oh wow, I have not gotten an email. I'm doing after school. But I'm sure every class we're trying to. Yeah, so you can come after school so we can talk about it. Okay. Sorry, they were just, I was like keeping a list in my head of things and I was like, okay, that's what it's thinking. I just had it. Coming back. Algebraically, you guys tell me. I need to get you guys talking about something productive. Algebraically, how do we do inverses?
Switch
And notation, what does an inverse look like? F.
F of negative, no. Oh, G of F.
That's how we verify it, but what's the notation for an inverse? It's F with a little.
-1.
That does not mean
Reciprocal.
multiply or to the power of or reciprocal. All right, we got them all. Graphically, how do we do inverses?
You switch that to
No, graphically. Across?
X equals
So x equals y equals x, or the identity function, right? We flip it. Okay, now numerically, what do we do? Since the domains and ranges switch with the order pairs?
switch as well.
Yeah, it's as easy as that. If you have order pairs, if you have like a table, you just gotta switch them. So if you have an original function of 2x minus 3, his inverse function, 1/2 x plus 3, which you would have gotten if you had algebraically, you could have gotten from there to there by switching x and y and solving for y. You could have gotten there. But can you guys see the pattern with all the points? What's the pattern with all the points? Yeah. And that's what the graphically thing was showing. So for any AB, if you can find a point on one graph, all you gotta do is there. There's the inverse one. So if you could just get a few points, hey, like a parent function, or like a transform function at a few representative points, all we gotta do is switch, and then we go. So, order pairs, switch, domains and ranges, switch, algebraically, switch the x and y, solve for y. This big man, I cannot speak today. This orientation thing is throwing me off more than I thought. Graphically, as a result of that switching. As a result of all the switching, we have that weird symmetry too. So, if you guys were to have a picture like this, and they were like, hey, is it an inverse? What could you do? Draw what?
Draw the middle.
Because we know that windows can be skewed, windows can be off from our graphing calculator handbook, right? So we have to make sure, and to make sure that's exactly what I would do. But if you were graphing your y equals x line, and if life was better than it was, and it went through the origin like it was supposed to, it sure looks like it's an inverse, right? If I was to draw the line perfectly. But what's another way we could check on our graphing calculator, or if they were to give us like some sort of graph we could manipulate? We could go ahead, plug in some point like what you guys just saw. Going x equals 1, y would be -1. And then we could plug in x equals 1 as a value of our other graph. Hold on, no, we couldn't plug in x equals 1 to check him. What would we plug in instead? -1. And if we plugged in -1, it sure better be a +1, or else there is no way this is an inverse. But it is. We could do that with any points we wanted. If we found 1 point on this one, flip it and check it over there. Found 1 point on this one, flip it. That flipping though is where it gets complicated. Not so much right now, but soon. Speaking of that flipping though, didn't we just talk about how that one parent function was an x cubed, and then we were thinking about, okay, he has an inverse function, we can see his graph, we can flip him across the y equals x line to find him. Here's the problem. Even if a function to begin with passes the vertical line test, so he is a function, even if a certain equation, a certain relation, passes the vertical line test, he is a function. If we're flipping him across a y equals x line, will his inverse always be a function also? And the sad answer to that one is no. As you guys are kind of setting up this page, let me give you an example. One of the most common dudes, or he's fine on his own. He has a function, or he has an equation, is a function, so totally fine. But as soon as you go looking for his inverse, we come up with a problem. As soon as you go looking for his inverse, we come up with a problem. So you guys are setting up this page where we have this weird adjective thing. It's just an adjective. One-to-one or invertible. It's a description of a special type of function. So a function, only functions can be one-to-one or invertible, and not all functions are. It's a special adjective. Special description, only for functions whose inverses are still functions. Now I want you guys to see, before I even graph it, the algebraic problem. So if I've given you, now I don't even have to just say y equals. I can use function notation because he is a function. He passes the vertical line test. I'm allowed to use f of x is equal to x squared. How would you algebraically, well, we can start by filling this in. Here's an example of an inverse. Well, let's wait. We'll get back. We haven't started talking about inverses yet. I'm giving you an original example. How would we algebraically find his inverse, guys? So that means that we would get y equals x squared becomes x equals y squared. Right? Then what did that lead us to?
Equals square root of x.
You have, right? Is he supposed to use a square root? Do you guys agree? To get y alone? here's the dilemma. When we square root, technically we square root that side, but we also square root this side. And this is what a lot of your Algebra 1 teachers might not have shown you. What's the square root of y squared? 4. Nope. You're half, right? It's a minus 2. Huh? Kind of. But that's not plus or minus. Actually, that is the absolute value of y. What does an absolute value do? Always keeps it an expression, whatever, positive, right? What does square root of y squared always do? Make it positive. Because if you put in a negative to this, what's going to happen? It gets squared, it becomes a positive, square rooted. It keeps the magnitude, but it loses the sign. So if I plug in a negative 4, don't I get out a positive 4? Because it'd be positive 16 square rooted. If I plug in a negative 25, ooh, okay, that'd be huge. But I would get out a positive 25. This is keeping everything positive. So that's technically how I would rewrite it. Now, do you guys remember from the olden days, how do we solve absolute value equations? To take out the absolute value, what do we have to put on the other side? It's been too long. To take out an absolute value in an equation, what do you have to put in on the other side? Now Dylan, here's your answer. Now he's plus or minus. So y was Nathan's answer only partially right? Why is the y equal to plus or minus root x? Not because of some magical thing you should remember. It's the math. When you square root both sides to undo the square, this guy isn't quite as simple as a lot of you guys thought. He's absolute value, which means to get rid of that absolute value, I need a plus or minus on the other side. Now here's the dilemma. I can't write this as f inverse of x equals. Even though I told you at the beginning of class we have to switch the x and y, solve for y, replace it with the inverse. I can't write that, and here's the reason why. What happens if I flip this guy across the y equals x line? Follow my trick. Ready? Take one little piece up to the line, and then just flip him. There we go. Close enough, right? Then take another piece and flip him. Ish, right? And then take the other piece and flip him. Cat whiskers. That's a little awkward. Oh, wait a minute. I see what happens. Instead of going this way, what's he going to be doing? So it's going to be a sideways parabola. Okay, it's a little bit messy to get there, but long story short, there we go. We got him. He's a sideways facing parabola. What's the problem with this student? Or does he not pass the vertical line test? So not every single function every single graph that's a function on its own will have an inverse that's also a function. And here's an example. In the algebra, I need a plus and minus together to make the entire thing. Now, I can say something like part of the f inverse is just this positive square root, or part of this f inverse is a negative square root. I can label pieces of the inverse as a function. That's legal, because that on its own, square root of x, that passes the vertical line test. That on its own passes the vertical line test, but I can't fully encapsulate, or else it fails. So here's what this whole thing up here is talking about. Since there are functions whose inverses are not functions, we have this special descriptor for functions whose inverses are functions. In order to be a function, the inverse would have to pass the vertical line test. In order for the inverse to be a function, he'd have to pass the vertical line test. And we don't want to have to go graphing every single function and then flipping them all and then asking ourselves, okay, does he pass the vertical line test? Instead, it'd be a lot easier to say, in order for this guy to pass the vertical line test, what would the original have to pass? The horizontal test. Now this is where it gets really tricky, because now you're like, great, there are two different line tests and I have to keep them straight. Nice thing is you've been learning vertical line tests longer, ever since Algebra 1. So hopefully it sticks out more for you. But this special adjective, a one-to-one function, an invertible function, in the math, it's nice. Because switching x and y, solving for y, won't have a nasty plus or minus in it. So algebraically, we can tell these one-to-one invertible in that there's no plus or minus. That'll occur. That helps a little bit. But some of you would have totally forgotten the plus or minus anyway, so you wouldn't have realized. So then, graphically, you can think, okay, well, my original function has to pass the horizontal line test, so when I flip it, then this will pass the vertical line test. But we can also look at it in tables, and we can look at it, well, we already talked about the equation thing. So, in tables, it's going to be a little weird. Because instead of just looking for each x to be paired with one and only one y, we're going to have to be looking at the y's also. Because now it also has to go the other direction. Now, this was something that honors got kind of confused, so I want to make sure that you guys have it okay. The graphs are pretty easy, I hope. For instance, how many of the graphs are invertible, guys? 1 or 2 or none? Just 1. I agree, Sid. He's the only invertible one because what's wrong? Oh, we just talked about somebody like him, right? What's wrong with him? He fails the horizontal line test, which means if I flip them, yeah. So he's a no-go. Now, pause. He's a function. But he's not a one-to-one function. He's a function. He passes the vertical line test. But what we're checking for is he this extra description of one-to-one or invertible? Nope, not that guy. That guy's fine. He's a function and he's invertible. What about this guy? Is he a function? Does every x go with one and only one y? Yeah, seemingly, right? But does every y go with one and only one x? Oh. So this guy is a function, but he's not one-to-one. He is a function, but he's not one-to-one. And if you were to graph, oh, he's a squared again, okay, lame, whatever. We get it, the quadratics, they all fail. But looking at the table, you can look and see if the y's are paired with one and only one x. So horizontal line test, everything is flipped. I'm looking at a horizontal line, and I'm looking at the y column. Okay. That's something that, like in deeper, higher theory math, it gets kind of important. For us, it's more of just like okay, it's a vocab thing. We're talking about inverses. We can kind of call them by their full names. Not just a function and inverse, but a function and inverse is a function. It's just kind of like a little extra. But this is where we kind of need to get to make sure you guys are good for the homework. After Nikki's question. Go for it.
So invertible basically just means reflected on the y equals x axis.
Invertible means when you reflect a function, that inverse will still be a function. So it's not so much that we are reflecting them per se, because that's how we find the inverse is reflecting or switching x and y. But this is just a special description, an extra additional classification of function, where he's already a function, that's good, but if I switch x and y and solve for y, that is a function. And functions are important because, like in your calculator, we talked about this a little bit, I think, during chapter 1a. Isn't it important for your calculator to only take questions that have one answer? Does that make sense? Why do some people like math better than, now I'm saying some, you don't have to tell me what camp you're in. Why do some people like math better than, like, I don't know, history? There are different ways to solve it, but you're all theoretically getting to the exact same answer, the set answer, the solved answer, the truth statement that like no one can question. Whereas if you're in any other class, what are they? Debates, right? The idea that truth is relative, whether or not it's actually true. Like when you get into philosophy, or even when you get into the Bible and people's different stances on it, I'm not saying it is relative, I'm just saying a lot of people debate that. When you get into history or into politics or even into finances or into, like, everything's debatable. Now, I'm not saying everyone's perspective is true or right, but once again, everything's debatable. In your calculator, it's important that it only has in its programming questions that it allows you to ask where it can give you one answer. That's kind of what functions are. They're like, give me something, I'll give you one answer. Not two, not three, not four. I'm going to give you one. And in this one, we're talking about invertible functions. We're saying, hey, not only is the function that way, but if we were to invert it, that will also be that way. Just kind of can we get into some math, just playing with some math? There's been a lot of theory. There's been a lot of like terminology. A lot of ideas kind of getting flipped or undone. Let's just get back to math. To be honest, kiddos, in homework, when you see, check whether or not it's 1-to-1. Some of them are super easy, like number 1. Why should this one be super easy to answer letter A and say definitely no? It's a parabola. It's going to fail, but and if you flip it, no. Is it a function? Yeah. Function notation, totally fine. Is it inverse a function? No. So why is letter B weird? I just said it doesn't have an inverse. We didn't say it didn't have one. We just said it didn't have one that was a function. So when it says solve, don't be like, I don't have to solve. You do. Just be aware something weird's going to happen. Okay. So, sorry, you were trying to tell me how to go. Okay. What am I doing? Switch to X and Y. X equals. Keep it legal or else stuff's going to get messy. Now what?
Square both sides.
Square root both sides. And when you square root both sides, you get the absolute value of y minus 2. Did you guys pick that up today? Square root of squared is an absolute value. How do we get rid of an absolute value?
Add the plus.
I can say y minus 2 is equal to plus or minus root x. Remember in equations, I'm totally allowed to say a equals b, the same thing as b equals a.
Subtract or add to both sides.
So y is equal to. Why am I not writing f inverse of x?
Because
What do I have?
plus or minus.
I have two different functions coming together and they fail as a function. I can't write function notation if it's not a function. But here's what I can do is write f inverse of x, and I can choose one to get the general idea. If they were going to tell me I had to make an inverse function, I could only choose half of it. Now here's the problem. This is the inverse relation. But you would need to do something like label it inverse, because otherwise it gets confusing, because the y could be that, or the y could be that, and that gets a little weird. I could label that with a word and say inverse. I could label it with a name, relation. But if I was to need to do a function like something where give me one input, I'll give you one output, I'd have to choose one of the signs. Now they haven't given me any like, hey, just a hint, this point is on the part that I want, so we can't necessarily say which one, we'd have to kind of guess. So this is probably the best answer as far as that's the inverse, but if they did want a function, okay, we can only choose half. Now how do I verify it's correct? Yeah, I have to do that whole little f of g and make sure it undoes. And if it does undo, remember, it goes all the way back to x. It takes away any squaring, any subtracting, any addition, any square rooting. All of it goes away except for x. Now, I wanted to get to number 2, because remember how I told you sometimes it might get tricky, the whole switching x and y thing? What about this guy? Hold on, first of all, is he invertible? You guys know what he looks like. Maybe we'll put a question mark and come back to him. Remember how the math told me there was a problem? I can think about the graph, and I can think about it failing the horizontal line test, but if I don't know the graph, let's go look at the math. Sound good? Okay, so let's switch x and y. Someone tell me why I'm afraid you might get stuck.
There's 2 different ones.
Oh, look at that. And what are you guys supposed to be doing? Solving for y, and the y's in the numerator and in the denominator? This is kind of dumb, but this is one of my, not that the problem's dumb, I mean it's hard. But this right here is one of the biggest things I want you to take away from Precalc. Not inverses, but given something hard, not giving up. You guys have math students. think of something that might make this easier. It's not going to necessarily in your brain get you all the way to the right answer, but are you willing to take a step? What do you want to do? Yeah. Yeah, the division is messing everything up. I don't want division, so get rid of it. But it's not going to work. I don't care. Do something. Don't just sit down and cry. Do something. Do something. So many kids just see it and they're like, wait for it. Do something. Get rid of it. If you don't like the division, then multiply. But that doesn't help. I don't care. Do it. Sometimes all you need is to look at it from a different perspective or to have it rearranged. Would you know to do something? But that was perfect, Vanessa. Get rid of the division. It's messing everything up. And some of you are like, well, I don't care if you see where it's going. Keep doing things. See if you can change it. Now what? What's something else I can do? Okay, now, think ahead. If you subtract 5, have you made it nicer in any way, shape, or form? Not really. I mean, we could subtract 5. I don't mind. So you have the 2y plus 1. I'm just trying to get you to look. We have to undo the problems. So if we subtract the 5, you're right. In some ways, we have this y kind of more isolated, but the problem is, who are we forgetting about or ignoring? Okay, so do something over here. I had to undo the division to try to break it down. Try to break it down more. Yeah, undo your multiplication, but in a way where you're doing it, but you're trying to break this guy apart as much as possible. You're going to get 2xy plus x minus 5 equals negative 1. Now, some of you are like, it's getting worse and worse, but in my mind, it's getting better and better. Because now I have my y terms free to roam about as they want. Now, but they're free. They're not in denominators. They're not in parentheses. So if the y terms are free, get them together, because isn't that the point? Don't divide. But what can you do? Making it too hard. Just subtract. It's okay. It's okay if you get stuck on this. I'm not mad about getting stuck, but having tried things. Play with it. Why do you go in math? Your brain's not always going to see the clear path. You just got to start taking steps. If it doesn't seem right, or if it seems like it's worse, back up a little bit and try another one. Why did I want to break apart all the multiplications, all the parentheses, all the divisions, and get the y terms on one side? Because now I can factor out a y alone, a y that will be isolated in one spot in my equation that I can then get all the way over. Just check it. Negative 1 minus 2x. I have x minus 5. With one division, I'm done. You guys see it? But I had to break it down. I had to break it apart. And breaking apart an equation is sometimes getting all the way back to adding and subtracting. And then rearranging and saying, aha! Now you're on one side. Aha! Now you're factored out. And with one division, I can get my... Have you guys gotten any weird pluses or minuses to tell me that it's not 1-to-1? So therefore, it is 1-to-1. Check. And my inverse function would be... Does anybody see anything weird? Doesn't look an awful lot like this one with all the signs to it. That's weird. It was the same. Woo! Alright, kids. Have fun. Tackle this homework. Come tomorrow with questions. I don't see any of these questions. No, we're good.
I ran to
Hi guys. If you pass by the smart board, just lay hands on it or something. No.
This is why coming up.